This is TRAPPIST-1e, an exoplanet 39.46 light-years or 12.5 parsecs away from us in the TRAPPIST system. Till date, almost 5,500 exoplanets have been discovered. Now, a major question that has been driving science in recent times is there life on any of these planets, especially on planets similar to Earth, the so-called Earth twins? To answer such a question, we would first need to know how would we go about detecting life on an object other than Earth. One of the ways is to search for chemical compounds called biomarkers such as water, carbon dioxide, methane, and ozone in the atmosphere of the planet. Another important compound is oxygen, which is the main focus of this video's paper. Hello everyone and welcome to Positive Delta. Rodler and Morales released a paper in 2014 about the results of the studies they have been conducting, where with the help of simulations, they tried to gauge the effectiveness and limits of the detectability of oxygen in the atmospheres of Earth twins around low mass stars. Basically, via numerous simulation, they tried to find the appropriate values for the parameters necessary to detect oxygen in the atmosphere of the Earth twin. The main reason that O2 was selected as a probe was that in 1993, Sagan et al. Found that because of the several absorption bands of O2 in the near and infrared regions of the spectrum, the compound acts as a strong indicator of the presence of oxygen-producing life. Two specific bands, the O2A band at 760 nanometers and the O2B band 1208 nanometers. There have been similar studies before this, but these authors are extending those experiments by accounting for atmospheric refraction effects in the transmission spectra and including random noise to the simulations. They had also included the expected performance of three extremely large telescopes, a range of spectral resolutions, and a range of stellar relative velocities and spectral types. How did the authors conduct the simulations? I will just briefly mention some key points and will not dive into the details since the video would then become too technical and I want to reach out to a broader and more general audience with these videos. To perform the studies, the required parameters are 1. Model transmission spectrum of an Earth twin, a similar transmission spectrum of Earth itself, another spectral emission of the host star, a configuration of telescope and an instrument setup, and white and red noise observational noise models. The model spectra look like these, where the top panel is the model transmission spectrum of the Earth twin, the middle is that of Earth, and the bottom is of an M4V star. The authors have considered stars with spectral types M1V to M9V. The main reason is that it will be easier to detect the transmission spectra of an Earth twin around the star of a smaller radius. Cutting the long story of methodology short, the authors tried to answer a few questions using these experiments. The questions include: at what spectral resolution will the spectrographs have the highest detectability of the molecule? What are the limitations imposed by the relative velocity between the star and our Earth, and how can we mitigate them? The number of transits needed to achieve at least a 3 sigma detection in the presence of white and red noise. The first one, the authors found that the optimal spectral resolution for the ELTs to detect O2 appears to be at R equals to 80,000, corresponding to the best trade-off between the slit losses and the spectral sparing of the Earth twin signal. The IS here stands for image slicer, which is a device used to enhance the efficiency of light collection and improve the signal-to-noise ratio in the observations. For comparison, the authors included an image slicer and found that it improves the efficiency significantly. The second one is one of the factors that the efficiency of detecting the molecule depends upon is the number of lines of O2 observed in the spectra after the light passes through the Earth's atmosphere. Since our atmosphere has the same lines at the same wavelength positions of O2, the lines in Earth twin spectrum will be detected only if the lines are Doppler shifted with respect to our lines by some amount. This shift can be simulated by introducing a relative velocity between a star and Earth and observe the fraction of lines that would appear blended. The authors found that the highest number of lines will appear blended when the relative velocity between the host star and the Earth is between plus or minus 15 to 30 km per second for O2A band and plus or minus 85 to 65 km per second for O2B band. The next factor that plays a key role in observing a binary system, by which I mean one object orbiting another, is the minimum number of transits required for extracting meaningful information from the observations. Here they have considered a 3 sigma confidence as a benchmark. The plots shown on the screen depict the number of transits required to measure the 760 nanometer O2 absorption band with 3 sigma confidence, taking the distance of the system from the Earth and the stellar type into account. The importance of this test becomes clear when you realize that if, for example, the orbital period of the planet is 1 year, then for a system with M4 star 10 parsecs away, 50 long years of observations will be needed to achieve a minimum of 3 sigma confidence. And that is without the inclusion of red noise. If you do include the noise, then the simulations get worse as the time factor of 4 to 8 will be multiplied. Along with other rigorous tests, the author finally conclude that successful measurements of O2 in Earth-like atmospheres with ground-based instruments will be most likely limited to host stars of spectral types later than M3V, which are located at distance lesser than 8 parsecs. The simulation then demonstrated that a 3 sigma discovery of O2 in the atmosphere of such a planet would require several years of observing time at ELTs. This is the entire gist of the paper. Please let me know what you have thought about it. Please do like and share the video and subscribe to the channel. If you have any questions, do leave them behind in the comments. Thank you and stay curious.